Today, I'm going to give you one last example, one last classical example of parameterized algorithms that use randomization. And then I'm going to switch to approximation algorithms, which is the last part of this course. So the last classical example I want to talk about is feedback vertex set parameterized by solution size. And let's say that we have an undirected graph. So I have some undirected graph G in the input, and I have some number K. And I want to know if I can remove K vertices so that the resulting graph doesn't have any cycles. So I want to remove K vertices to kill all the cycles. We've talked about this problem in many formats before, but now we want to use both parameterization and randomization. So when we were talking about kernelization, we came up with some kernelization rules here, right? So we talked about what happens if we have vertices of small degree. So we had some reduction rules. And the first reduction rule was that if I have a vertex of degree 0, that vertex is not really going to contribute to any of the cycles. So I can just remove that from my graph. Similarly, if I have a vertex of degree 1, there is no way that that vertex can be part of a cycle, so I can just remove it from my graph. So my first reduction rule was that if the degree of some vertex V is less than or equal to 1, then I just take my instance GK and I turn it into G minus this vertex and K. I'm not putting the vertex into my solution. Now, another simple rule was that if I have a loop, then that's a cycle that only contains one vertex. So I definitely have to put that one vertex into my feedback vertex set. So my second rule was if I have some vertex V and I have a loop, then I just take my instance, which was GK, and I just remove V, but I add it to my solution. So now I have to find a solution of size K minus 1. Now, what if we had a vertex of degree 2? So this was our third reduction rule. Our third reduction rule was that if I have some vertex U, and let's say that its only neighbors are V and W, right? Then any cycle that goes through U has to go through both V and W. And so I can just remove U and add a direct edge between V and W. Because it never makes sense to put U into my solution. I can always put either V or W in the solution instead of putting U. So in this case, I take my instance GK and I turn it into G minus U, but I have to also add an edge from V to W. So I say union with the edge VW, and my K remains the same. Okay. But these reduction rules are not really enough. So let's say I apply all of these reduction rules as many times as I can. I apply them exhaustively. What does this tell me? I'm basically removing loops. I'm removing every vertex that has degree 0, 1, or 2. So I just know that the degree of every vertex is at least 3. That's all these reduction rules would give me. And now knowing this, I want to find a randomized algorithm. Now, suppose that you want to find a feedback vertex set, a small set of vertices whose removal kills all the cycles. And of course, you want it to be as small as possible. And let's say you want to take the vertices randomly. What probabilities would you intuitively give to every vertex? So let's say I just want to pick some vertex randomly, and I want to say this vertex goes into my solution set, right? But I don't want to pick them uniformly at random, of course, because that basically ignores the entire graph. But if I have a graph, do you agree that it makes sense to take vertices of higher degree with more probability? Because if I have a vertex and the degree of that vertex is larger, that vertex is probably going to be in a lot of cycles, right? So we want to kind of formalize that. But here's the thing, instead of taking a vertex and saying that I take each vertex in proportion to, with a probability that is in proportion to its degree, I can just say I take an edge randomly, and then I take one side of that edge. That's kind of the same idea, right? Because if I just pick an edge randomly and then I pick one side of the edge, then I expect that every vertex is picked with a probability that is proportional to its degree, right? So let's say that's my algorithm. So after I apply all of these rules and I cannot apply any of them anymore, I just pick some edge uniformly at random, and then I just pick one of the two endpoints of the edge. And I say I put this endpoint that I chose randomly into my solution. So this is my random algorithm for feedback vertex set. Let's call my function R. So my function first just applies these rules, apply these as many times as possible. So I just apply all of these three rules exhaustively. And after this is done, the next step, let me put R here, maybe so that I have more indentation. And of course, I have some G and I have some K. Okay. So after I do all of this, the next step is just pick some edge in the set of edges of G, and pick the edge uniformly at random. Okay. And then, well, this edge is going to have two endpoints. Let's say the endpoints are U and V. So let's say my edge was an edge UV. Okay, what do I do with this? So I just say with probability half. So just flip a coin, and let's say that I put my coin flip result in C. So C is just uniformly chosen from 0 and 1. And then I say if C is 0, if my coin was heads, let's say, then remove U. So just take your instance GK and turn it into G minus U and K minus 1. So I'm removing the vertex U, and I'm also putting it in my solution. Otherwise, remove the vertex V. GK just becomes G minus V and K minus 1. So this is my randomized algorithm now. So I just try my reduction rules from kernelization, and as far as I can apply them, I do. And when I fail to apply them, I just pick a vertex uniformly at random and remove it. And of course, after I do all of these things, I don't have any space here to say, but I go back to the top. And then again, I try to apply these rules. And whenever I fail to apply these rules, I just pick a vertex randomly. So just imagine that here there is a go-to that goes back to up here. Okay. So this is now my randomized algorithm. Now the question is, what is the probability that this algorithm actually succeeds, assuming that we have a feedback vertex set of size K, right? This basically looks like a heuristic, right? So I'm doing the best I can, and as soon as I see that I cannot do anything else, I just say do something random. Okay. So here's the thing. I want to prove a lemma that says if I pick this edge here uniformly at random, then the probability that I actually have an edge that is connected to my feedback vertex set is going to be at least a half. So this is what I want to say. This is my lemma. I want to say let X be a feedback vertex set of G. Okay. Now I can of course say that I want X to be an optimal one, but we'll see if we need it. I think I will not need it. I can just work with any feedback vertex set. So let X be any feedback vertex set of G. And let's say that I've already applied all of these rules. So I know that the degree of every vertex in G is at least 3. So, and for every vertex V in G, the degree of V is at least 3. Now I want to claim that when I pick this edge E, there is at least a half probability that I'm picking an edge that has at least one of its endpoints in X. So another way of saying it is that at least half of the edges in G have at least one endpoint in X. Have an endpoint in X. So I want to prove this. Or in other words, I want to say that if you just pick an edge uniformly at random, there is at least a half probability that that edge is connected to your solution X. So your solution is just a subset of vertices, right? Because it's feedback vertex set, I want to remove a subset of vertices. Okay, how can I do that? Well, let's just have some figure. As usual, let's say that I have my solution here, which is X. And let's say that I have the rest of the graph, and let's call that Y. Now, what are the edges that have at least one of their endpoints in X? There are either edges that are entirely inside of X, so they have both of their endpoints in X, something like this. Or there are edges that are going from X to Y, right? And what are the edges that don't have an endpoint in X? Those are the edges that are entirely within Y. So I want to say that the number of edges that are entirely within Y is less than the number of edges that go from X to Y, or plus the number of edges that are entirely in X. Okay? Now, I also have this assumption, of course. I know that the degree of every vertex is at least 3 because I have already applied my reduction rules. Okay, so let's do a simple thing. How many edges can I have in Y? How many edges can I have that have both of their endpoints in Y? So here's the thing, X is a feedback vertex set. So after I remove X, there is going to be no cycles remaining. So there are no cycles in Y. So Y is a forest. And if Y is a forest, then in every forest, the number of edges is less than the number of vertices. Okay, so this is the first thing I know. I know the number of edges in Y is at most the size of Y minus 1. And it can be exactly Y minus 1 if Y is connected, if Y is a tree. Okay, so all I have to show is that I have at least Y minus 1 edges outside of Y or between X and Y. Okay, so let's forget all the edges that are entirely inside X, and let's just count the edges that go between X and Y. I'm going to show that even they are enough. I don't even need to add the edges that are entirely in X. Okay, so here's the thing. I have some tree here. And of course, I have a bunch of edges from this tree, which is on the Y side, to the X side. But how many edges do I have? So let's say I take, for example, a leaf of this particular tree in this forest, right? In my original graph, I know that every vertex had a degree of at least 3. This leaf has only degree 1 inside of y. So it must have at least 2 edges that are going out to x. Right? So for every leaf in y, I have at least 2 edges going from this leaf to x. Okay, that's the case of leaves. What happens if I have a vertex of degree 2 in y? So when I say degree 2 in y, I mean it has 2 neighbors in y. So for example, let me just connect this to this, and let's consider this vertex. Again, in the original graph, it had a degree of at least 3. Right? In y, it only has a degree of 2. So it has to have at least 1 edge that goes from y to x. Okay, so this has to have at least 1 edge going to x. But I also have a bunch of other vertices, and these are the vertices that already have degree 3 or higher in y. I can't say anything about these guys. They might have all of their edges in y. Right? So the only thing that I can say here is that the number of edges between x and y is greater than or equal to the number of leaves in y times 2 plus the number of degree 2 vertices in y. Okay, so let's just use a notation. So I write y less than equal 1 to mean the vertices in y that have a degree of at most 1 in y itself, basically leaves. Okay, or I mean, I can also have an isolated vertex. I count that too, because an isolated vertex will also have 3 edges to x. And then I write y2 for vertices in y that have a degree of exactly 2 in y. And for the rest of it, I just write y greater than or equal to 3. So this subscript is the degree in y itself. So basically, what I know is that the number of edges between x and y is greater than or equal to twice the size of vertices in y that had a degree of 1 or smaller, sorry, plus the number of vertices in y that had degree 2. Okay, I know that I have at least these many edges. Okay, but now just forget the rest of the graph and just look at y. Y is a bunch of trees, it's a forest, right? These are the leaves. Y2, you can think of this as vertices in your graph. If you just root your graph at some point, y2 are the vertices that have exactly 1 child, because they have degree 2 in the tree, they have their parent, they have 1 child. Okay, so you can think of these as the leaves, you can think of these as vertices that have exactly 1 child. And then this part, the ones that have a degree of 3 or larger, these are vertices that have at least 2 children, maybe more than 2. Right? But from basic graph theory, we know that in every tree, the number of leaves is greater than or equal to the number of vertices that have 2 children or more. You can prove this inductively, right? Because if I just start at some root, initially I just have this one, which is a leaf. And if I make the degree of this one to be larger than 2, so basically I'm adding 2 new leaves just to get 1 non-leaf, right? And then again here, if I make the degree of this one 3, I'm adding 3 leaves just to have 1 more non-leaf. So you can just follow this and you can see that the number of leaves is always going to be larger than the number of vertices that have 2 children or more. Of course, I can have something like this that has only 1 child and doesn't change anything, but I'm not counting that. So in other words, I'm just saying that this set is larger than this set. Okay. So how does it help? Well, this one is larger than this one. And here I have 2 of this. So instead, I can just say I take 1 of this and I take 1 of this. So the number of edges between x and y is greater than or equal to the number of leaves plus the number of vertices that had 2 children or more, and I just keep y2 there. Okay, but now y was divided in 3 parts, and I have all 3 parts here. So this is just the size of y. Okay, so what did we prove? We proved that the number of edges that are entirely inside y is at most y minus 1. But the number of edges that go between x and y is at least y. So the number of edges that go between x and y is more than the number of edges that are entirely in y. So more than half of the edges have at least one of their endpoints in x, right? Because I'm not even counting these ones. Okay, so how can I use this lemma to analyze this algorithm now? So I'm applying these rules, and after I apply these rules, I just see that if I pick some edge uniformly at random, with probability half, that edge is going to have at least one of its endpoints in my solution x, right? But then I'm also taking the endpoint uniformly at random. So at the end of it, when I'm removing one vertex, there is at least a 1/4 probability that the vertex that I'm removing was actually really in my solution, right? So I have a half probability when I choose the edge, and then I have another half probability when I choose the endpoint. Okay, so let's just see what happens in this whole algorithm. I'm basically removing vertices one by one, and of course I never remove more than k vertices, because if I run out, if k becomes 0, then I just say I failed, right? So I'm removing vertices one by one, and some of the vertices are removed with these rules, and when I was removing them, I was sure that I had to remove them. That's fine. So some of the vertices that I put in my solution are like this, and when I'm putting it in the solution, of course I had to do this. There was no choice here. That's a correct choice. Okay, but some of the vertices that I'm putting in my solution come from here, but each one of them were correct with probability at least 1/4. And I'm taking k vertices, so the probability that all of my choices are correct is at least 1/4 to the power of k. This is my probability of success, right? So every time that I run this algorithm, I have 1/4 to the power of k probability of success. So again, going back to our basic techniques in randomized algorithms, if I just run this algorithm 4 to the power of k times, then I will succeed with constant probability. And if I just do it 4 to the power of k times log n times, then I succeed with very high probability. Okay, so my overall runtime is just going to be 4 to the k times the runtime of this thing. Now, what is the runtime of this thing? You can figure it out. It's polynomial in n. Actually, I think it would probably be linear. It would be n plus m, where n is the number of vertices and m is the number of edges. But again, I'm too lazy to do it. So it's polynomial. That's all we care about. So it's going to be FPT, and the dependence on k is just 4 to the power of k. Great. So now I'm going to go to the next module, and we're going to talk a little bit about approximation algorithms. And we will hopefully see examples of approximation and randomization, and approximation and parameterization combined with each other too. So this is our last module in the course, approximation algorithms. And again, this goes back to the story that I've been telling you many times. What happens when I have a problem and the problem is too hard? For example, it's NP hard. what can I do with that problem? So some of the things that we have already seen is that, well, I can try some sort of randomized solution, or I can parameterize it by some parameter, maybe say that the problem instances that I care about have some nice property. But now we're going to look into the third approach, which is just approximating. And until this point, I was mostly talking about decision problems. So normally our problems just had a yes or no answer. But of course, when I'm talking about approximation algorithms, I have to talk about optimization problems. So you're given some input, you want to create some output, and every output has a particular, let's say, cost. And you want to, of course, find the optimal output, the output that has the smallest cost. But that's NP hard, or that's hard for some other reason. And then you just try to find an output that has a cost that is as close to optimal as possible. Okay? And this is the basic of approximation algorithms. So let's say I have some optimization problem. And let's call it P. Now, how can we formalize an optimization problem? So when we had a decision problem, our input was just a string, and the answer was either 0 or 1. In this case, our input is going to be a string. Our answer is also going to be a string, right? And then we have a cost function, which takes the input and our output and says how well we did, right? So my input is just some string. Let's call it, I don't know, let's just call it I, which is in sigma star. And I have to create some output. Let's call this one O, and this is also in sigma star. And I also have some cost function. Let's call this one C. And what it does is that it takes the input and it takes the output, and it just gives me a cost, which says how good my output was. Okay, so it maps it to some cost. And basically, well, I can say that this is from sigma star times sigma star to, let's say, all of our costs are positive and real numbers. Okay. Now, what is my goal? My goal is that given a particular input, I want to find the output that minimizes the cost function. Or if I have a maximization problem, I can say I want to find the output that maximizes the cost function, right? So let's say that the optimal value for this cost function, I just show it with C opt. Okay, so C opt, optimal cost of I, is just going to be the smallest possible cost. So I'm going to say it's going to be the minimum over all outputs O of the cost of this input and output pair, right? But now for technical reasons, the minimum might not exist. So yeah, whatever, let's call it, yeah, maybe I can take the infimum instead of the minimum. I wanted to see if I can do something cleverer, but no, let's just take the info. Okay. Or of course, on the other hand, if I have a maximization problem, if I want to maximize my cost, then the optimal cost is just going to be defined as the maximum, or in this case, supremum, over all possible outputs of C of IO. Okay. So now we know what our optimization problem is. And of course, I want this cost function to be computable. right? Because if I can't compute the cost, it's just weird. I don't know how close to optimal I am. Okay, but now let's define what an approximation algorithm actually is. So I want to define the concept of an approximation algorithm with some ratio, and let's call that ratio rho. Okay, so what does it mean when I say, for example, I have an approximation algorithm with ratio 5, or an approximation algorithm with ratio log n? This rho doesn't have to be a constant number. So for example, we've already seen like a 7/8 approximation for max 3 set, right? What does that officially mean? It means that I have some algorithm A, and for every possible input in sigma star, if I take the output of my algorithm, so let's call that O of A. Okay, and if I take the optimal output, okay, the ratio of the costs is going to be at most rho. So the cost of my input and the output created by A over this input divided by the cost, the optimal cost of I want this thing to be at most rho. Okay, but again, I have this problem that I have both minimization and maximization problems, right? So I want to have a definition that handles both. To do that, I just say, let's take two cases. Let's take this number and let's take its multiplicative inverse. And let's take the maximum of these two. And let's say that this has to be at most rho, and it has to hold for every input I. Okay. So this is just a nice trick that people use a lot. So when I'm talking, let's say, about a 2 approximation, does that mean that my cost is at most twice the cost of the optimal, or at least half of the cost of the optimal, right? I can just handle both of those cases here based on whether my optimal was a minimization optimal or a maximization, right? So with this terminology, actually, we no longer have a 7/8 approximation for 3 set. We have an 8/7 approximation for 3 set. So this rho is always going to be at least 1 with this definition. But yeah, it makes things nicer. We only talk about approximation ratios that are greater than 1. And what we mean would be clear based on whether we're solving a minimization or a maximization problem. Okay. So, but this is just defining a single approximation algorithm, which I called A, with approximation ratio rho. But usually what we're looking for is not just a single algorithm that gives us a single approximation ratio. We're usually looking for a family of algorithms. So usually what I want to do is that I want to give you some number, and let's say I give you the number rho, and I say, give me an approximation ratio, give me an approximation algorithm with ratio rho. And basically, I want you to have a scheme, a system or a family of algorithms that can give me any possible approximation ratio. And of course, if I want better approximations, it's going to take more time. So I'm fine if my time depends on the approximation ratio. In a sense, it's kind of similar to what we were doing in parameterized algorithms, where we were analyzing the runtime not only based on the size of the input, but also based on some other parameter. But now you can think that this other parameter is just how good our algorithm is going to approximate, how close our ratio is to 1. Okay, so I can just define this like this. So I can say that an approximation scheme is just, you can think of it itself as an algorithm, or you can think of it as a family of algorithms. But the approximation scheme takes some precision epsilon, which is greater than 0, okay, and produces an algorithm let's call that algorithm A epsilon, that solves my problem. My problem was called P, within an approximation ratio of at most 1 plus epsilon. Okay, so now instead of just having one algorithm, you can think about it like I give you an epsilon, and for every epsilon, you give me an algorithm, right? Or alternatively, you can just think that your algorithm doesn't only get the input instance, it also gets that epsilon, like a parameterized algorithm. So you can just think of it as a single algorithm that takes an input instance and some epsilon, and then solves that within a ratio of 1 plus epsilon. But of course, we care about the runtime of these algorithms, right? So until this point, I'm just saying, this is the ratio, this is what an approximation scheme is. But it's not useful to just have these things if I don't have any bounds on the runtimes of my algorithms. So here we have things that are in a sense similar to XP, and then something that is kind of even stronger than FPT. So first, we have the concept of a PTAS, and this stands for polynomial time approximation scheme. Okay, so I want to have an approximation scheme that takes polynomial time. But what do I mean when I say it takes polynomial time? I mean it takes polynomial time with respect to the size of the input, with respect to n. So let me just say that the size of my input is n. But it can basically have any dependence on epsilon in the same way that an XP algorithm could have any dependence on the on the parameters. So I want to say that an approximation scheme is a PTAS if for every epsilon greater than 0, there exists some constant, let's call it C of epsilon, which depends on epsilon, such that the runtime of my algorithm, T of A epsilon, when run on the input I, is bounded by n to the power of C epsilon. Okay, so again, this is very similar. It's basically the same thing as the definition of an XP algorithm. So if you fix your epsilon, you're going to have a polynomial time algorithm, right? But the degree of the polynomial can depend on the epsilon. So this is called a PTAS. Now we have another thing which is called FPTAS. And FPTAS stands for fully polynomial time approximation scheme. And by fully polynomial time, I mean that it's polynomial not only based on n, but also based on epsilon. Okay, but it doesn't make sense to say it's polynomial based on epsilon, because ideally I want this epsilon to be a very small number between 0 and 1, right? And I want it to actually be really close to 0 ideally. So if I want my epsilon to be small, I can't really say I want something that is polynomial time with respect to epsilon. But if epsilon is positive and it's very close to 0, then 1 over epsilon is going to be a large number. So maybe I can say that I want my algorithm to have polynomial runtime with respect to n and 1 over epsilon. Okay, so as I reduce epsilon, my algorithm gets more accurate, gives me a better solution, but it's also going to take more time. And I model that by the fact that 1 over epsilon is going to increase as I decrease epsilon. So an approximation scheme is an FP-TAS if I can write something like this. I can say for every epsilon greater than 0, or actually, okay, if there is a polynomial P, if there exists a polynomial P such that for every epsilon greater than 0 and for every input I, which has length n, the runtime of my algorithm with parameter epsilon over this I is at most this polynomial, but the polynomial can take 2 different variables, and one variable is n, the other variable is 1 over epsilon. Okay, so this is an FP-TAS. So if I want to give you some examples, let's say here, if I have, let's say, an algorithm that has a runtime of O(n) to the power of 1 over epsilon, right? This would be a p-TAS algorithm. Because for any fixed epsilon, this is polynomial time. But of course, the degree depends on epsilon. But if I want an FP-TAS algorithm, let's say I have an algorithm that takes n squared divided by epsilon to the power of 5. Okay, this is polynomial time with respect to n and 1 over epsilon. So if I have an approximation scheme like this, I would call it an FP-TAS. Okay, but this is just the complexity theory that we have here. But let's talk about some actual problem. And as usual, let's talk about our favorite problem, which is vertex cover, if you don't know already. So let's say I want to do vertex cover. Now, remember when I was talking about parameterized algorithms, I had to always say what my parameter is. Now that I'm talking about approximation algorithms, I have to always say what my cost function is, right? And my cost function is, again, just going to be the size of the vertex cover. So I want to minimize the size of the vertex cover. So I can call this minimum vertex cover. So I give you a graph G, and I want you to choose as few vertices as possible so that they cover all of the edges of G, so that any edge in G has at least one of its endpoints chosen. Now, again, the difference with the parameterized case is that in the parameterized case, we had some parameter K, and we just wanted to decide whether we have a vertex cover of size K or not. Here, we don't have a parameter. We just have some graph as the input, and we want to figure out what is the size of the vertex cover, the smallest vertex cover, and of course, it's NP-hard. So we want to approximate it. So maybe I want an algorithm that gives me, let's say, 5 times as many vertices. So it gives me a vertex cover, but it's not optimal. It has maybe 5 times more than it should have, right? Or maybe the approximation ratio is not constant. Maybe I have an algorithm that gives me log n times optimal. So yeah, give me some heuristics. What would you do if you just want to solve vertex cover and if you don't have any parameter? Like, how would you choose vertices to put in your vertex cover? Now, a very kind of trivial solution would be to just try to pick vertices that have the highest degree, right? So I just pick the vertex that has the highest degree, or if I have many vertices of highest degree, I pick one arbitrarily, and I say I put this one in my vertex cover. And I remove it from the graph, and I remove all of its edges from the graph. And then I just continue this. Every time I pick the vertex that has the highest degree. Now, eventually, I will cover all of my edges. Eventually, I will get to an empty graph. So of course, I'm going to get a vertex cover. But of course, it's not minimum, because if it were minimum, then I had solved an NP-hard problem in polynomial time. But now the question is, how far can it be from optimal? And actually, the next homework will come out soon. And one of its problems is that you have to show that this simple algorithm is not going to give you a constant approximation. So it's not an approximation with constant ratio. And the way you're going to show that is that you're going to come up with some counterexamples that shows that if you apply this algorithm, you will get really large vertex covers. Okay, but what is an actual algorithm that gives us constant ratio? So again, there are many parallels with what we were doing in parameterized algorithms. So if you remember what we did, like at the very first sessions of parameterized algorithms, the idea was that I just took any arbitrary edge and I said that, well, this edge has to be covered. So I have to either put this endpoint of the edge into my vertex cover or this other endpoint into the vertex cover. And then I would just do branching because I had a bound and I knew that I want a vertex cover of size at most k. Now here I can do the same thing. I can just do branching. But the problem is I don't have a bound on the size of my vertex cover. So if I do branching, I will get a branching tree that has depth n. So I get like exponential runtime 2 to the power of n. That's not something that I like. But can I just do something stupider? Like, let's see. I have, let's say, an edge from vertex u to vertex v. I know that I have to take at least one of these two vertices into my vertex cover. And I just want to approximate it. I'm fine with taking like a constant value more or some constant factor times the optimal. So I just take both of them. Okay, so very silly algorithm. I just take an edge arbitrarily, not even at random. I just take any edge. And I take both of its endpoints into my vertex cover. And I remove both of its endpoints from the graph, and I remove all the other edges that were connected to these vertices. And then I just continue the same thing. I pick another edge, I take both of its endpoints. Now, intuitively, whenever I'm taking an edge, I had to take at least one of its endpoints, and I'm just taking both of them. So this should give me a 2 approximation, right? But let's see if we can formalize that. And actually, I'm going to formalize it in 2 ways. So I'm going to give you 2 different proofs that this is a 2 approximation. And the reason is that these techniques will be used for many other problems. So, okay. The first way of doing this is that I can just do induction. Let's say I do induction on the size of my graph. So number of vertices plus number of edges, right? For a graph that is small, so if I have just one vertex or just 2 vertices and 1 edge, it's obvious that I have a 2 approximation. So the base case is trivial. Now, let's say that I have some graph G, right? What am I doing? And let's say that my algorithm gives me some cost. So I'm just going to write C of G for the cost of my algorithm over the graph G. So C of G is just the number of vertices in my vertex cover using this very simple algorithm. And I also write C opt of G for the optimal one. Okay. So if I take a graph G and I take an arbitrary vertex, what do I know about the optimal solution? I know that at least one of the 2, sorry, an arbitrary edge, at least one of the 2 endpoints of this edge has to be in my optimal solution. So the optimal solution for G is going to be greater than or equal to 1 plus now either the optimal solution of G minus U or the optimal solution of G minus V. So 1 plus the minimum of the C opt of G minus U and C opt of G minus V. This is what I know about the optimal solution. Even though I don't have an algorithm to actually compute it, I just know that it satisfies this inequality. What do I know about my own solution? I just know that my cost is basically 2 plus the cost of G minus U minus V. So I'm just removing both of them. Right? Now I just want to do induction on the size of the graph G and show that I always have C of G less than or equal to 2C opt of G. This is what I want to prove inductively on the size of G. Okay, so I already told you about the base case, that's trivial. So let's just use this formula. So C of G is 2 plus C of G minus U minus V. But I can just use induction and say that this is at most 2 plus 2C opt of this, because this is a smaller graph and my solution on this smaller graph is at most twice the optimal solution. Now, here's the thing. This is the graph G where I've removed both vertices U and V, right? But here, I have the graph G where I've only removed vertex U. Here, I have the graph G when I've only removed vertex V. So I can say that this inequality is greater than or equal to 1 plus the optimal cost in this smaller graph when I remove both vertices. Right? Because of course, if I have a smaller graph, if I have a subgraph, I have either a smaller vertex cover or a vertex cover of the same size. It's not going to happen that I remove a vertex and my vertex cover gets larger. That's weird. Okay. So now let's continue here. I know that the cost of G is at most 2 plus twice the cost, the optimal cost of G minus U minus V, but this is just twice this, right? Because this is greater than or equal to 1 plus C opt. So this is going to be less than or equal to 2 C opt of G. So I just proved inductively that whatever solution I find is at most twice the optimal solution. Okay, this was the first proof, but now I'm going to prove it in a different way without induction. Oh, and by the way, what is my runtime before that? So every time I'm just taking an edge and I'm just removing both of its endpoints. So overall, I'm just removing all of my edges and all of my vertices. So it's linear time. It's just n plus m. Okay. Now let me give you another proof that this is a 2 approximation. So I just say, look at all the vertices that I put into my solution using this very simple algorithm. So what am I doing? First, I'm finding one edge, let's say from U1 to V1, and I'm putting U1 and V1 into my solution, right? And then I'm removing both of these vertices from the graph. Then I'm finding another edge, let's say from U2 to V2. And I'm removing both of its endpoints, and so on. And let's say until I do UK and VK. Now here's the thing. Look at these vertices in my original graph before I did any of the removals. Of course, they had an edge because I'm not adding any edge at any point, right? But also, I will not see any vertex more than once here, right? Because when I picked this edge, I removed both U1 and V1 from my graph. So U2 and V2 are going to be different from U1 and V1 and so on. So in my original graph, I basically have these K edges and they're completely separate from each other. They don't have any vertices in common. So just to cover these K edges, I have to choose at least K vertices, right? For each one of these edges, I have to choose one of their endpoints. But what is my algorithm doing? It's just taking 2K vertices. It's taking both endpoints. So my algorithm is a 2 approximation. Okay. So this is the basic approximation for vertex cover. But now I'm going to look at another problem, which is actually an extension of vertex cover, if you think about it. And this is a problem that had an appearance in a previous homework. So let's talk about set cover. Okay. So what's set cover? This is not writing very well. So in set cover, I have some set, let's call it S. So in my input, I have a set S of, let's say, n elements. Okay. And other than this, I also have a bunch of subsets of S. So I also have, let's call it M. I have M subsets S1, S2 to Sm, and all of these are subsets of S. Okay. Now, what I want to do is to choose some of these subsets, and by the way, they can be the same. It's not like they're not distinct subsets. But I want to choose some of these subsets so that they cover the entirety of my original set S. Okay? So my goal is to choose, let's say, a set of indices. Now, because they're indices, I'm going to show it with I, but it's not inputs, it's indices now. Choose some I, which is a subset of 1 to M, such that if I just take the union of all the elements, all the subsets whose index is here, so if I just take the union of Si for I in I, this union is S. So it covers everything. Now, what is my cost? My cost is just the size of I, and I want to minimize it. So I want to take as few subsets as possible from the subsets that are given to me in the input, so that I cover all of the elements in my main set S. Okay, this is called the set cover problem. Now, again, one of the homeworks will definitely ask you about the relationship between set cover and vertex cover, because they're very much related. But let's ask something else here. So let's say I just want to, again, find a heuristic, find a greedy algorithm, try my best without having a proof that it actually works. What would I do? So, and of course, again, this is an NP-hard problem. You can prove it, but I'm not going to do it. So let's just say that we all agree that this is an NP-hard problem. So we don't think that there's going to be a polynomial time solution. Now, what would you do? So let's say that you just want to greedily have a heuristic that takes some of these subsets. Which subset do you prefer to take first? Yes. So, well, I'm talking only about the first subset. You're a little bit faster than what I expected, but okay. So if I want to take the first subset from this list, I would take the subset greedily that covers the maximum number of elements, right? And then after I take that subset, let's say that was Si, then all of the elements in that subset are already covered. So I can remove all of those elements from S, and I can also remove them from all the other SJs. Okay, so this is my greedy algorithm. I say as long as my set S is not empty, just take the largest Si. So let's say Si, let it be the largest subset. Put Si in the solution. And then just remove all the elements that are covered by this Si. So S becomes S minus Si. And for every J from 1 to M, Sj also becomes Sj minus Si. And I might get some empty sets, but that's fine. Okay. So this is a basic greedy algorithm. Now, why would this work? Now, again, a part of your homework is to show that this is not a constant approximation. But I'm going to show you that it is a logarithmic approximation. And this was actually used in the previous homework, in homework 1, I think. So the homeworks are really important. Do the homeworks. Okay. So I want to show you that this gives an algorithm with an approximation ratio that is O log n. So the logarithm of the number of elements. Okay. How would you analyze an algorithm like this? So when we were talking about the approximation ratio, we were always talking about what happens in the optimal algorithm, right? So we want to see how many sets are taken by the optimal algorithm. Now, of course, we don't have the optimal algorithm itself, so we cannot compute that, but we can use it in mathematical reasoning, right? So again, my algorithm is just this, but everything I do here is just mathematical analysis of its runtime and its solution, right? So let's say that my optimal cost is T. Okay, so I'm fixing some input, and I'm just saying, just assume that if I had the optimal algorithm, I would need to take T subsets. Okay, now, and let's say that the number of subsets that I actually took is K. So let's say my actual cost here was K. This is the number of subsets that this greedy algorithm takes. I just want to find the ratio between K and T. Okay, but here's the thing. I want to see how many iterations this while loop can go through. Because in every iteration of this while loop, I'm putting exactly one of the subsets into my solution. So if I can just analyze the number of iterations, I also have a bound on K. Okay. So how can I analyze the number of iterations? So when you want to show that a program terminates, or when you want to show that a program terminates within some given time, you usually just find some ranking function, which is a function that decreases at every iteration of this while loop. So if I have a value and that value decreases every time that I run this while loop, and if that value cannot decrease forever, then I can say that this while loop cannot run forever. Okay, so what's decreasing in this while loop? Yeah, the size of the set S, the number of elements, because every time that I cover some elements, I'm basically removing them from S and I'm removing them from all of the subsets. So of course, I know that the size of S is decreasing every time, and the size of S is originally n. So this while loop can run for at most n iterations. So this shows that my k is at most n. But that's not a good enough analysis. I want to have a better bound on k. Okay, and actually I want a bound on k based on t. So let's see how much decrease I have here. Because it's not like every iteration of my algorithm decreases the number of elements by only one, right? Sometimes it decreases it by a lot. And actually, I'm always taking the largest possible subset. So I'm always decreasing it by as much as I can. Okay? So I just want to find the bound on the size of this SI, because the size of SI at this point in time, not its original size, but at this point in time is the amount that I decrease. Okay, so here's the thing. I know that my optimal solution is going to take T subsets, right? So what does this tell me about the size of the first subset that I remove? So just take the first iteration of this algorithm and take this subset that I'm removing. What can I know about its size? So here's the thing. Let's say I have my optimal algorithm here, and I have my greedy algorithm here, right? And let's say that the first set that I took in my greedy algorithm was SI1. Okay, so this 1 is the number of the iteration in the while, and SI is just SI. Now, here, I know that I could just take T different sets, and those T sets covered all of my main set S, right? So here I have T subsets. Now, what can I say about the size of these T subsets? If I have T subsets that are covering n elements, then I can just use the pigeonhole principle, and I can say that there is at least one of these subsets that is covering n over T elements, right? So at least one of the subsets here, one subset chosen by the optimal algorithm, has a size that is greater than or equal to n over T. Okay, but what am I doing in my greedy algorithm? I'm taking the largest possible set, right? So SI1 was the largest possible subset that I could take in the first iteration of my while. So, and I know that there is one subset among the subsets that the optimal algorithm took that had this size. So my largest subset should also have at least this size. So SI1 is greater than or equal to n over T. But now I can do the same analysis for every iteration of this algorithm, right? So basically, the fact that this was just analyzing the first iteration of the while loop doesn't really matter, right? If at some point I have some number of elements, let's say my number of elements is now, I don't know, n prime instead of n, after a bunch of iterations, right? Again, I know that the optimal algorithm is covering these n prime elements with at most T subsets, right? And actually it's going to cover it with like even fewer than T as we go through these iterations, but at most T. So the optimal algorithm definitely finds a subset that covers n prime over T elements, right? And then the subset that I'm taking, which was the largest possible subset, is also going to cover at least n prime over T. Okay, so how would I formalize this? Well, actually, let's just keep track of the size of our set, the remaining size of my set. So let's say that n0 is just n, And let's say N1 is the size of the set after I do one iteration of this while loop. N2 is the size of the set after I do two iterations, and so on. So what do I know about Ni? So at the ith iteration, before it, I had Ni minus 1 elements, right? And I know that there was an optimal solution that covered all of these elements with at most T subsets. So there was a subset in the optimal solution that had size Ni minus 1 over T, right? So the subset that I'm removing here has at least this size. So my Ni is less than or equal to whatever I had before minus the size of this subset that I'm removing. Okay? Or again, with some basic algebra, I have that Ni is less than or equal to 1 minus 1 over T times Ni minus 1. Okay? So at every iteration of this while loop in my greedy algorithm, the size of my set is getting multiplied by this number. Okay, and this is a number that is smaller than 1. So my set is really getting smaller and smaller. Now, of course, the weird part here is that this number actually depends on the cost of the optimal algorithm. And I don't have the optimal algorithm, but I can use it in my analysis anyway. Okay. So if we just solve this, it's easy to show that Ni is less than or equal to 1 minus 1 over T to the power of I times N. Right? Okay. But this just tells me how many elements I have at every iteration of my while loop. But when does my while loop end? My while loop ends when my set is empty. Or in other words, it ends when the number of elements is less than 1. Okay, so I have to find a K. So this is what I want to do. Let me just erase this part. I want to find some value for K such that Nk is guaranteed to be less than 1. Because if I find that, I know that at my case iteration, I no longer have anything. And because I don't have anything in my set, I've already covered everything. Okay. So, but I have that formula there. So I want to find a K such that, okay, that's the thing. Nk has to be less than 1, but Nk was at most 1 over 1 minus 1 over T to the power of K times N. I want this to be less than 1. Okay. Now from this part, it's again just algebra. And I'm going to write it from here because I'm very bad at doing calculations and I always use Wolfram alpha, and you should too. Okay. So I have this thing. And let's just play with it a little bit. So this is T minus 1 over T to the power of K is less than 1 over N. Right, so I'm just expanding this part and I'm bringing the N to the other side. Now let's just take the logarithm of both sides. So I will just have K times log of T minus 1 over T is at most, minus log of N. Okay, let's just multiply this by minus 1. So I get log of N is less than, and here when I'm multiplying by minus 1, I can just swap T and T minus 1. So K log of T over T minus 1. Okay, and finally, I can just say that k has to be larger than log n times 1 over log of t over t minus 1. Okay, so if I choose a k that satisfies this inequality, then I can be sure that my algorithm terminates with a solution of size at most k. Now, I don't want every k that satisfies this, I just need one k that satisfies this inequality. Okay, now this is the part where you use Wolfram alpha. You take this part and you ask Wolfram alpha, is this less than t or not? And it takes the derivatives and computes the minima and maxima and everything and tells you. So, and it turns out that for every t that is greater than 1, this part, 1 over log of t over t minus 1 is less than t. Okay, so if I just choose my k, so let's say I choose k to be log n times t, because this thing is smaller than t. I just need something that is larger than log n times this thing. So I just choose log n times t. And let's say I put a +1 just to be sure. Okay, so if I choose k to be this, then I can be sure that the answer that my greedy algorithm finds is at most k. So, but this was the optimal answer. So my answer is at most log n times the optimal answer. Of course, you have a +1 as well, but that doesn't really matter that much. You can just say O log n times the optimal answer. Now, well, we can have some fun with Wolfram alpha about this. You see, if I want to find better bounds here, instead of taking the log, which, well, when I write log, I just mean log base 2, right? But instead of log base 2, you can just try different bases of the log here and see which bases work. Okay. Oh, and one more point. This doesn't work for t equal to 1, but t equal to 1 is obvious. It's just like the case where you have a subset that covers everything. So just do that separately, and this whole algorithm works. Okay, but anyway, if you try on Wolfram alpha to give this log different bases, you will see that any base that is up to e, up to the natural log would work, but nothing larger than e actually works. Okay, so you can choose k to be the natural log ln of n times t plus 1, and the same analysis works. Now, what happens if you see a problem like this in your final exam and you don't have Wolfram alpha? So let me just give you a solution that doesn't use this black box part, but gets the same bound. And it's based on the inequalities that we have used so many times. Okay, so let me just this. Let me see, do I have it here? Should I do it myself? Oh, no, I have it here. Okay. So this is the expression that I'm working with. And I want to choose a value of k so that this expression becomes less than 1, right? Because this was the size of the remaining set. Now, here's the thing. We have this nice inequality which says 1 minus x is at most e to the minus x, right? So we use this inequality all the time. Here I have 1 minus 1 over t, so I can just say this is at most e to the power of minus 1 over t. But then I'm also raising it to the power of k, so it's e to the power of minus k over t, right, times n. And I want this thing to be less than or equal to 1. So yeah, I want this to be less than or equal to 1. How would you do this now? Yeah, just take the log, right? So if I just take the log or the normal ln, I can say that this ln of e to the minus kt times n has to be less than or equal to 0, right? And what is this? Well, it's just ln of n plus minus k over t. Okay, so minus k over t. So it's not equal to 0. Okay, and this gives you exactly the same thing as before. Well, k is at most like t times ln of n. Okay. Nice. So this is all for this session, and we ran out of time. So I'll see you next week, and we'll talk about more approximation algorithms. Have a good day. Bye.